Let's get started on today's notes over quadratic inequalities. The first thing we're going to do is graph some quadratic inequalities on the coordinate plane. Here are the steps that you're going to follow in order to graph those inequalities. The first thing you have to do is define the boundary for the inequality. So we're going to graph the parabola that defines that boundary. Then we're going to use a dotted line when the inequality does not include the boundary line. So for example, in an inequality, your symbol might look like this, greater than or less than. You're going to use a dotted line or a dashed line, and you're going to use a solid line when the inequality includes the boundary line. So your symbols will look like this, greater than or equal to, less than or equal to. You're going to shade the area above the quadratic boundary line when the inequality is greater than, so greater than or equal to, and below when the inequality is less than or equal to. So those rules are actually outlined in this table right here. This shows you what type of line to use and your shading. And because it's an inequality that we're going to be graphing, we're going to have a solution set, right? It's not just like x equals, it's going to be x is greater than or equal to, right? You've got those inequality symbols, so on your graph, you're going to have some shading. So let's get into this example 1. Here's an example of a quadratic inequality that's in standard form. So y is greater than x squared minus x minus 12. So recall that standard form is just y equals ax squared plus bx plus c. It's just written in that form. And when it's written in standard form, we can factor it. And you're going to be doing a lot of that today. So the first thing that I notice is y is greater than. This symbol right here tells me that I'm going to use a dotted line or a dashed line, whichever you want to write. A dotted line, and I'm going to shade above. And I just like to write that down as a little reminder of what I need to do when I graph. So the first thing we're going to do, and I'm going to change colors here, is find that boundary line. So I'm going to graph this quadratic as if it was y equals x squared minus x minus 12. The first thing I'm going to do is I'm going to find the zeros of this. Now every example that I am going to do today is factorable. So we're actually going to be able to factor each one of these quadratics. When I factor this quadratic, I need two numbers that multiply to negative 12 that have a sum of negative 1, and that's x minus 4 times x plus 3, which means I have zeros at x equals negative 3 and x equals 4. Right? So I'm just finding the solutions, right? Or the roots, the x-intercepts, if you will. And I'm going to go ahead and graph that on this coordinate plane. There's where x equals negative 3, 1, 2, 3, 4. There's where x equals 4. So that is where my quadratic will cross the x-axis. All right, here's my x-axis, here's my y-axis. So those are my zeros. Now, I need 3 points, or when I'm graphing a quadratic, it's good to have the vertex. So now we've got our zeros. Now I'm going to find my vertex. How do I find the vertex? I know the x value of my vertex, which is also the axis of symmetry. Remember, that's that vertical line that splits that parabola in half, is negative b over 2a. That's that formula. X equals negative b, that's going to be positive 1, over 2a, which is 2 times 1, right? So 1 is A, negative 1 is B, negative 12 is C. So that's 1/2. That's the x value of my vertex. How do I find the y value? I plug in x. What do I get for y when I plug in 1/2 for x? 1/2 squared minus 1/2 minus 12, and I get y equals negative 12.25. Okay, 1/2 squared, that's 1/4, minus 1/2 minus 12 is negative 12.25, or 12 and 1/4. So I know my vertex is 1/2, or you know what, let's just write it as decimals. let's do 0.5 and negative 12.25. So that's going to look like this. I'm sorry, 0.5 and then negative 12.25. That's like right down here. That's going to be off my grid just a little bit. Now, one of the things that you can always do, and I like to show this because I can graph those, I can graph this parabola with these 3 points, that vertex and those roots, but I could also graph it with my vertex and perhaps my y-intercept using the properties of quadratics. So the y-intercept is when x is 0. So if I were to plug in 0 for x, that's 0 squared minus 0 minus 12, and I get y equals negative 12. So my y-intercept is 0, negative 12. 0, negative 12 is like right here, right? Because that vertex is negative 12.25. So if you think about it, right, that axis of symmetry, oh, I moved in too much. Oh my gosh. That axis of symmetry splits that parabola in half. So if I go up just a quarter of a unit and 1/2 to the right or left, I can do the same thing to the right, right? Because of the axis of symmetry. It's like your line of reflection. So now what I'm going to do is I'm going to graph this boundary line. And because, let me make this a little bigger, it's going a little bit slow here. Because that boundary line is greater than, I know that it's just going to be a dashed line, just like this, right? It's not going to be solid. It's going to be dashed because it's not or equal to. It's just that. Now, which way do I shade? I'm going to shade above for greater than and below for less than. This is a greater than symbol, which means I'm going to shade above. So I say to put your pencil on that quadratic and go up, which means it's going to look like this. There's where y is greater than this quadratic, this boundary line, x squared minus x minus 12. Let's move on to example number 2. This is another quadratic inequality that we're going to graph, and this one's in vertex form. So I love vertex form because it already gives me my vertex. And that vertex is at, if you recall your quadratic transformations, this quadratic, right, which is like your parent quadratic function, like y equals x squared, your vertex is going to move right 4 and up 8, which means your vertex is at 4, 8. 1, 2, 3, 4, and then I'm going to go up 8. So there's my vertex right there. Now when I look at this quadratic, I know that right here, if I have a negative out in front, I know that it's going to open down, right? So I'm just going to write this down. This opens down. So that vertex is a maximum. I also know that it's a vertical stretch by a factor of 2. Let me just write that down. It's a vertical stretch by a factor of 2. So how am I going to graph this? I know the pattern of a quadratic. I'm going to go out 1, up 1, right? In this case, a vertical stretch by a factor of 2, I'm going to double that vertical value. So I'm going to go out 1, and I'm not going up anymore. I'm going down. Instead of out 1, down 1, I'm going to go out 1, down 2. What I do to one side of it, I have to do to the other. And then instead of out 1, down 4, I'm going to go out 1, down 8. So that's actually my x-intercepts right there. And then I'm just going to graph it. So now let's look at the boundary line. Okay, this is a greater than or equal to. So I'm going to use a solid line. And because it's greater than, I'm going to shade above. So let's first graph that boundary line. It's a solid line because of this or equal to. That line underneath tells me I'm going to have a solid line. Whoop. And that greater than tells me that I'm going to shade above. So what does shading above look like when I have an upside down parabola? Remember, you can put your pencil on that line and go up. Boom. So it's everywhere like outside, if you want to look at it like this. All of this is the solution set for this quadratic inequality. And that's how you would graph that quadratic inequality. Let's move on to the next set of examples. And in these examples, we're going to be solving quadratic inequalities. So you'll find that on these next two examples, you're not going to see a y. Okay, you're only going to see one variable, and that's an x. And here's the steps that you're going to use to solve. You can refer to these steps whenever you're working on your assignment. The first thing you're going to do is move all terms to one side, and you're going to set it equal to 0. Then you're going to solve it. You're going to factor it, use the quadratic formula, etc. Everything today will be factorable. So all examples, everything on the assignment, all will be factorable. I'm just going to write that down. Factorable. Okay. Factor if you are able. Okay. Then you're going to write solutions as critical values. You're going to plot these on a number line. Those are your critical values. And those critical values will divide your number line into intervals. I'll show you what this looks like. You're going to pick a value within each interval to test, and then you're going to write your solution. Okay, so let's move on to this first example in this set, which is example number 3, quadratic inequalities in one variable. So as you can see, I do not have a y. I have x squared minus 3x minus 7 is greater than or equal to 3. So the first thing I'm going to do is move this 3 to the left side, right? That'll move all those terms to one side, and I'm left with x squared minus 3x minus 10 is greater than or equal to 0. And now I'm going to factor this. It's a basic trinomial, two numbers that multiply to -10 that have a sum of -3. Those numbers are -5 and +2. So my factors are x minus 5 times x plus 2. And that means our zeros are at x equals -2 and x equals 5. So what I am finding is where this quadratic right here is greater, or I'm sorry, I actually rewrote it. This quadratic right here, where is this quadratic greater than or equal to 0? Where are my y values greater than or equal to 0? Well, if you think about it, if it crosses the x-axis at -2 and 5, where in this interval, right, in these intervals, where are my y values greater than or equal to 0? Where is that graph or that parabola above the y-axis? Okay, so I know this parabola, if you were to like graph this in Desmos or on your graphing calculator, it would look like this. And when it cross, right, your x-axis right here at -2, at x equals -2 and x equals 5. So I can already tell you, hey, I know the solutions just given this, but I'm going to show you what you're going to do on all of the problems on your assignment. So what we're going to do now is I've plotted those points on a number line, and we're going to test some points within each interval. So these are critical values that break up this number line into, or this parabola into intervals. So I'm going to pick a number within each interval, and I'm going to test it on this quadratic. So for example, a number in this interval over here to the left of -2, that would be smaller than -2, is -3. So I'm going to plug in -3 into this quadratic right here. So I'm going to write test points right here. And we're going to test the point -3. So that's going to be -3 squared minus 3 times -3 minus 10. The question is it greater than or equal to 0? And actually, if you want, you could put it in this original, the original inequality right there, and you could do -7. Is it greater than or equal to 3? That will absolutely work. So -3 squared is 9. -3 times -3 is +9. So 9 plus 9 minus 10. Is it greater than or equal to 0? 9 plus 9 is 18. 18 minus 10 is 8. 8 is greater than or equal to 0. So that means the points in that interval, which would be from negative infinity to negative 2, are included. Let's test the next section. Anything between like a negative and a positive, I always test the point 0. It's a super easy point to test. So when I plug in 0, I'm going to get 0 squared minus 3 times 0 minus 10. Is it greater than or equal to 0? 0 squared minus 0. Negative 10, is negative 10 greater than or equal to 0? No, it's not. This interval is not included in my solution set. Let's move on to a number that's greater than 5, which would be maybe 6. Let's try 6. So I'm going to plug in 6 in for x. Now what I'm doing, I'm plugging it in for x right there and right there, right? So I'm going to plug in 6 squared minus 3 times 6 minus 10. The question is it greater than or equal to 0? 6 squared is 36. Negative 3 times 6 is negative 18, so minus 18, then minus 10. 36 minus 18 is going to be 18, and then 18, I'm sorry, right there, then 18 minus 10 is 8, and 8 is a number that is greater than or equal to 0. So that interval is included in our solution set. How would I write this as a solution? Okay, I'm going to write my solution in a different color. I'm going to write it in green. Remember, negative infinity is every point to the left, right, over here. So infinity goes to the right. If I write this in interval notation, remember I write it from left to right, I would say negative infinity to negative 2. Now, am I including the point at negative 2? I really like to put dots or open dots because this symbol says greater than or equal to. I am including these points at negative 2 and 5. Okay, these critical values will be included in my solution set. So negative infinity to negative 2, including, or positive 5, including, to infinity. Now, if you wanted to write this in as inequalities, your solution would look like this. X is less than or equal to negative 2, or x is greater than or equal to positive 5. So you could always write it like that. I tend to prefer interval notation. So let's move on to our last example for solving a quadratic inequality. And this is another example of a quadratic inequality in one variable. So the first thing we're going to do here is move all of our terms to one side so that we set this quadratic equal to 0, or greater than or equal to, whatever, greater than, less than 0. So the first thing I'm going to do, I'm going to move this to this side over here. So I'm going to get 3x squared minus 4x minus 7 is less than 0. Where is this quadratic less than 0? If I graphed it on a coordinate plane, where are my y values? Negative, right? Where is that parabola below my x-axis? And we're going to define it. Our solution is going to be the domain, right? Where in the domain is it? So this is a quadratic in standard form that it has an a value that's greater than 1. So I'm going to use this slide and divide technique, right? I'm going to factor it. So 3 times negative 7, I'm going to get x squared minus 4x minus 21, and I'm just factoring this. Now I need two numbers that multiply to negative 21 that have a sum of negative 4. Those numbers are negative 7 and positive 3. So I'm going to write those out like this: x minus 7 times x plus 3. And because I multiplied that a value into my last term, that first term into my last term, now I need to divide that a value out of each of these last terms. So I get, and I'm assuming that you know how to do this. If you do not know how to factor quadratics, I would suggest going back, and I'll put a little card up there in the upper right-hand corner. If you need help factoring quadratics, you can just click that link, and that'll show you some examples of how to factor different quadratics. And this right here, x plus 3 over 3, that becomes x plus 1. And now we have factored this quadratic. And here are my solutions. I'm going to have zeros at, and remember you set each factor equal to 0. My solutions are at x equals -1 and x equals 7 over 3, which is also, for you decimal people, it's 2.3 repeating, okay? So now we're going to take those critical values, our x-intercepts, our solutions, and we're going to graph them, or plot them, rather, on a number line. And my points are at -1, and let's just do 2.3 repeating, or you could say 7 over 3, whichever you want to write. So same thing, right? So now we're going to test some points within each interval. The first thing I'm going to do, which was not the first thing I did on the last one, is my symbol is less than, not less than or equal to, so I know that I'm not including these points in my solution. I'm going to put an open dot there, which lets me know that I'm not including those points. So now let's test some values. I'm going to test -2, which is in this interval. A number in between -1 and 2.3 would be 0. I'm going to test that point. A number greater than 2.3 repeating would be 3. I'm going to test that point. So now let's test some values, or test some points. The first one I'm going to test is -2. And I'm actually going to, in this example, I'm going to plug in these values into my original quadratic up here, but I want you to know that each of these will work, right? They are the same thing. So I'm going to plug it into the original. So the first one I'm going to plug in is -2. I'm going to plug in 3 times -2 squared minus 7. Is it less than 4 times -2? 3 times, well, let's see, -2 squared is 4. 4 times 3 is 12. So 12 minus 7 is less than -8. 4 times -2 is -8. 12 minus 7 is 5. 5 is less than -8. That is not a true statement, which means this interval is not included in my solution set. Now let's move on to our next interval. Okay, right? So I've got like these intervals right here that these critical points break up this number line in. So the next value that I'm going to test is 0. I'm going to plug in 3 times 0 squared minus 7. Is it less than 4 times 0? Remember, I'm just testing points. So that's why I like to put that little question mark there. Is it less than 4 times 0? Well, 3 times 0 squared is 0. 0 minus 7 is -7. Is it less than 4 times 0, which is 0? Yes, it is. So this interval right here from -1 to 2.3 repeating is included in my solution set. Now let's test the point 3. When I plug in 3 for x, I get 3 times 3 squared minus 7. Is it less than 4 times 3? 3 squared is 9. 9 times 3 is 27. Minus 7. Is it less than 4 times 3 is 12? 27 minus 7 is 20. Is it less than 12? No, it is not. So this interval right there is not included in my solution set. So now let's write our solution. How do we write our solution for this? Our solution in this case is going to be from -1 to, I'm going to write 7 over 3. So in interval notation, I'm not including the point -1. So I'm going to have a parentheses, -1 to 7.3, and I'm not including that point either, so I'm going to have parentheses there. Remember, if I had a less than or equal to, I would have a solid closed circle and I would be including, so I would have brackets. Now, how would I write this as an inequality? X is between the points 7 over 3 and -1. And so this is how I would write it as a solution, and in both interval notation and as an inequality. And that concludes your notes over quadratic inequalities. We graph some quadratic inequalities on the coordinate plane to show our solution set. And then we solve some quadratic inequalities. And in those examples, we only had one variable, and we set it equal to 0. We found our critical values. We factored and found our critical values and tested some points and wrote our solution. And that concludes your notes. I hope it was helpful.